Hey guys, it's Mr. Murray. We're talking about Chapter 4 right now. Chapter 4 is all about hydrocarbons, the diversity of carbon compounds, and effectively in kind of how I know it and how most folks know it, it's organic chemistry. So it's sort of the beginning of organic chemistry, but one of the things that's really cool about carbon, I know we were kind of really stoked about water last chapter, but here we get into carbon and why it's such a cool element, and why life is really dependent upon it. And so the big reason that life is dependent upon carbon is because of its ability to form this crazy diversity of organic compounds. And the reason for that is that carbon bonds 4 times. And early in the chapter, it starts to look at some of the diversity that you can get, even if you have only 4 carbons and hydrogens, right? So if I take these carbons, I make, this is called, if it only has carbons and hydrogens, the kind of a molecule it's called is you guessed it, it's a hydrocarbon. So if I have 4 carbons like this, so a hydrocarbon is a molecule that just has carbons and hydrogens, just to review. So if I have a molecule like this, it has single bonds between its carbons. Excuse me, I call it butane. So this is the stuff that they put into those lighters that you light your grill with. Butane, it's a hydrocarbon, so it burns really well. There's lots of energy in it. But what's cool about carbons and the way they bond is there's different ways to make this thing, right? And so I can make another molecule called isobutane, and isobutane is an isomer of butane. It's an isomer, excuse me. It's an isomer because it's the same thing, right? So if I look at these carbons and hydrogens and I count them up, I'm going to count it as C4H10, okay? Because I got 4 carbons, and if I count all those hydrogens, there's going to be 10 of them, okay? I can make isobutane by taking some carbons, and instead of putting them in a line like that, I'm going to put one branched off the top up here. And then I'm going to fill in hydrogens everywhere else that they can go. And by everywhere else they can go, what I mean is that every carbon here has to bond 4 times. So let's count them: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is still C4H10, but it's different. This is a different molecule than we saw up here. So that being said, we got butane and we got isobutane, and that's just the beginning of some of the diversity that you can get. When you start getting into more and more and more of these carbon atoms, you start to get more and more diversity. Another way to increase the diversity is to have double bonds between the carbons. Those double bonds could be in different places along the length of a hydrocarbon, and you could also put rings in there, okay? So there's just massive amounts of diversity. The best way to describe it is like, carbon is sort of like Legos. It just keeps on putting things together in new and interesting ways. Some other ways to make isomers, we already talked about one isomer. That was called a structural isomer that we just talked about. Another way to make an isomer is if I have those 2 carbons bonded together, I could have used what's up there, and I put different groups off them. Night, love you. I'm going to bed. Put different groups off them. So this is 2 carbons bonded together, and I put different groups off of them. Now, these 2 carbons are only going to need 2 other groups off of them. If I put the groups in the same place, I'm going to put some X's here. If they're on the same side, I'll put H's over here. They are said to be called cis isomers. So because these X's are on the same side, they're said to be called cis isomers. Or that is the cis isomer of this. And guess where this is going to be? It's going to be on the opposite side. Here's my X. Here's my other X. See, oops, sorry, that's an X. So because this X and this X are on opposite sides, it's not the same thing as a cis isomer. It's called the trans version of this particular isomer, okay? So the other way to do isomers is called enantiomers. Enantiomers are left and right-handed versions of each other. And I will show you one of those in the classroom, because the best way to show you that is with a model. So I have one of those hanging from my classroom. I'll bring it up to our new classroom. Why do we care? Well, we care because this is just the very beginning of the kind of diversity that we can see inside of carbon compounds. And we care about those that diversity because that diversity can lead to different functions of these molecules. So the structure is going to lead to the function. So if I change that structure, the function could very well change. So the next thing we're going to talk about is just the different kinds of functional groups. So we're going to quickly go over those. So those hydrocarbons that we just talked about, or any other kind of a carbon compound is going to have a bunch of different functional groups. And there are a total of 7 of these that okay, there's 7 different ones here that we need to know. The first one's called the hydroxyl group. The hydroxyl group is going to make something into an alcohol. So if we have a regular hydroxyl group like this, and we put it on a molecule called ethane, okay, so this isn't quite ethane. I would need another hydrogen right here to make it ethane, but we're going to make it ethanol. And to make it ethanol, we're going to add this functional group called OH. Okay, so now this is ethanol. This is what goes in. This is the molecule that's the active ingredient in things like wine and whatever else, the alcohol that people buy at liquor stores. Because of this functional group, that's what gives the drug its properties and how it interacts with people's brains. Next group is called a carbonyl group, and a carbonyl group comes off of a carbon. It looks like this. And because there's some questions here, like I don't know what's here and what's here, there's 2 kinds of carbonyl groups. The first kind is called a ketone. And with a ketone, this carbonyl group is in between things that go for a while. So we'll put H's here. Oops, here's another carbon with some H's off of it. So these are 2 methyl groups. I'm having a hard time drawing down there. Here it is. So this is a ketone called acetone. And it's called, so anyway, this is a carbonyl group. We need to remember that. And there's 2 ways to make carbonyl groups. One of the ways is right here, called a ketone. And another way you can do a carbonyl group is by putting it at the edge of the molecule. So here we go. And this is going to be an aldehyde. So this is the end. Let's circle this. So this is the end of this molecule. And we're going to put this on with 2 carbons. This is called propanol. It is an aldehyde. And so here's my O, here's my H. Because that C double bonded O is attached to a hydrogen and it's not in the middle of my molecule like I have there, I'm going to call it an aldehyde. Next group is a carboxyl group. This one's one of my favorites. So now we're going to start using this abbreviation R, and the R stands for the rest of the molecule. Oops. So the R stands for the rest of the molecule. So carboxyl group has a carbon double bonded to an oxygen with an OH group off of it. So this is sort of a combination of those two other ones that we just saw, right? So a carboxyl group has all of this going on for it, okay? This is going to be important because it's going to allow for bonding all over the place. Carboxyl groups tend to be ways that molecules bond together, okay? Amino groups, and then we're getting into amino acids here in just a moment. Amino groups look like this. But real quick, we're going to go back to carboxyl groups. Sometimes with carboxyl groups, they'll lose this hydrogen, and so they're called carboxylic acids, because if you remember from our last discussion, when something loses those hydrogen ions and puts them into solution, that increases the amount of them. So sometimes carboxyl groups are called carboxylic acids. So sometimes you'll see them written like here, and sometimes you'll see them written like this. And then there'll be like a minus sign there for that missing hydrogen. And that hydrogen's out there in solution. It's not really missing, it got dumped off somewhere. All right, this is an amino group. Amino groups tend to be bases, and they tend to be bases because they can look like this, what we have here, and they can also look like this. So they can grab hydrogens from solution. And so if they grab those hydrogens from solution, we're going to give them a positive charge, okay, on the group. So there's two different ways we can see these, okay? Because we're pulling hydrogens out of solution, that lowers the amount of hydrogens in the solution, and so amino groups tend to make bases. Okay, sulfhydryl groups. These are cool in proteins because sulfhydryl groups will stabilize proteins across their middle. Across whatever functional, so this SH group you'll find in amino acids, and a sulfhydryl group will reach across a protein to another sulfhydryl group and cause it to become much more stable across the protein. Phosphate group is our next one. Phosphate group is going to have P coming off of the rest of the molecule. And that P, this is a little bit tricky for me. Whoops, the P has, let's just do this all over again. The phosphate group is going to have a phosphate group, here we go, start again, is going to have an O, a P, and an O, okay. We're going to have double bonds here, I'm sorry, single bonds there, a double bonded oxygen on the top, and an oxygen down the bottom, okay? So if you guys remember, we had adenosine we had ATP in your freshman year. Well, there were three of these phosphate groups on ATP. Also, when molecules gain or lose these phosphates, it's a big transfer of energy thing going on inside of these molecules. Methyl is our last group. A methyl group has a carbon with some hydrogens off of it. This is very similar to the molecule called methane, except there's like this is the rest of the molecule over here, just like the rest of the molecule for a phosphate group would be here. And so a methyl group, what it's going to do is this is all very non-polar. There's some really nice sharing. And when I have these non-polar groups, they're going to start to avoid water, especially if they're around other non-polar groups. So that's the story with the functional groups. And that's it for Chapter 4. Thanks for listening, guys. We'll see you soon.